Well, welcome to QOD 27A, which arises as a result of having missed some time in class to talk about some things we would have otherwise talked about in class. And so, what we had been talking about most recently was constructing an electrochemical cell and talking about the separating the half reactions into the anode compartment and the cathode compartment, and then connecting them with a wire that we can use to conduct electricity, and also connecting them with a salt bridge to equal out to balance out the charges. And in doing so, we can create a cell which generates what's called electromotive force. That is actually the ability to do work using electrical energy, electrochemical energy. And so one of the things we're doing in chapter 20 is something that you'll see repeated a little bit later in the year, is going back and taking a look at a topic that we covered in chapter 4, but now looking at it in greater detail and more specifically in a quantitative way rather than a qualitative way. So in chapter 4, we learned how to use the activity series of metals to determine whether a particular redox reaction was spontaneous in a particular direction. Now we're going to do this quantitatively and use what are called standard reduction potentials to determine, which will also tell us which direction that a reaction is spontaneous in, but it will also allow us to calculate what's called a cell potential or electromotive force. Water is often used as an analogy for this. So if you've got a battery or a cell and it is generating an electrical current, depending on what that cell consists of, it is going to have a different, what we would call electromotive force behind it. So one way to think about that is, say, water in a hose, and the pressure behind the hose would sort of be how hard that water is being pushed out of the hose. That's one way to think about it. Another way to think about it would be, we have a waterfall here, and to think that water that is falling down a waterfall has a lot more energy and a lot more ability to do work. Say a gallon of water falling down a waterfall has a lot more energy and ability to do work than, say, a gallon of water running down your driveway as you're washing your car. And so these are sort of analogies of electromotive force. We also refer to this as cell potential, and in a minute I'm going to show you what the unit for this is. It's the volt. But electromotive force, again, is the idea of how much energy is there behind a certain quantity of electrons. And we also, for a cell, we'll call that cell potential. Well, the unit of cell potential is the volt. And the volt is defined, and so a volt is defined as that 1 volt is 1 joule per coulomb. The joule, as we know, is the SI unit of charge. The coulomb is the SI unit of, the joule is the SI unit of energy. The coulomb is the SI unit of charge. And none of these numbers are things that you need to memorize because they're all in the formula sheet. 1 coulomb is equal to 6.2 times 10 to the 18th electrons. What's probably more important and that you'll use more often is that a mole of electrons contains 96,485 coulombs. This number, 96,485, is what's known as the Faraday constant. And again, that is listed in the AP formula sheet. So you don't have to memorize that. One thing I do want to say about the volt is that the volt is an intensive property. So cell potential is an intensive property. It is energy per unit of charge. And so unlike things like energy, where when you scale up, say a reaction, you also multiply the enthalpy or the free energy of that reaction because it's an extensive property. Cell potential is actually an intensive property because it's not energy, it's energy per unit of charge. And as you scale that up, the energy goes up, but also the number of coulombs goes up, and so it winds up staying the same. So cell potential is an intensive property. It is the amount of energy per unit of charge. By the way, you may or may not have noticed this, but if you multiply these two numbers together, you get Avogadro's number, right? Because if you multiply electrons per coulomb by coulombs per mole, you would get electrons per mole of electrons, which would be Avogadro's number. Okay, let's take a look at this. So let's go back and see what we already know. We already know that we can use the activity series to determine which direction a particular reaction would be spontaneous. And so if I was going to make a cell out of nickel and copper, and so I had a half reaction in which I had nickel metal, a nickel electrode and nickel ions in one compartment, and another electrode in which I had copper ions and copper metal in that separate compartment. I can look at the activity series, look and see that nickel is higher on the activity series than copper. And so therefore it's going to be spontaneous in this top direction. Nickel is going to be oxidized because it's higher up. Copper is going to be reduced, but it's because it's lower down. Now we're going to talk about using something called standard reduction potentials, which will tell us the same thing, will give us the same answer to this question, but it'll also allow us to calculate a cell potential. So let me just show you that this table 20.1, which is from your textbook, is actually a distillation down of what is called Appendix E in the back of your book. And these are what are known as standard reduction potentials. And standard reduction potentials basically tell you how easy it is for a certain reduction half reaction to occur. So the more positive the standard reduction potential in volts, the easier that reduction is to occur. And so therefore, the reduction of fluorine to 2 fluoride ions is the easiest reduction that you could possibly do. On this table, the hardest reduction that you could do would be to take lithium ions and reduce them to lithium metal. Now, let me show you some. Now, you will notice that there are more things on this table than just metals. So far, when we talked about the activity series, we just talked about metals. But let me pick out a few metals that are on this table. Silver, copper, hydrogen, which we'll talk about why I'm talking about hydrogen in a second, even though it's not a metal. Silver, copper, hydrogen, nickel, iron, zinc. So I'm reading that from top to bottom. Silver, copper, hydrogen, nickel, iron, zinc. Now let's go back and look at the activity series. Silver, copper, hydrogen, nickel, iron, zinc, if I go from bottom to top. So, and that makes sense, right? Because the things that are at the top of the activity series are the things that are easiest to oxidize. They're the most reactive. The things that are at the bottom of a table of standard cell potentials, the things that have the most negative reduction potential for the half reaction are going to be the things that are the hardest to reduce. So the easiest thing to oxidize, the most active metal, lithium, is the hardest to reduce. And so that's why, and so you can, so actually you can make a activity series of metals simply by taking Appendix E or this table and looking at metals and just putting them in reverse order of what their reduction potentials are. All right, well, how are we going to use these numbers? We're going to use these numbers, number one, to figure out how to construct a cell, but then also figure out how to calculate its electromotive force. And so let's take a look at, I've now just distilled down that table 20.1 even further, and let's go back to the same reaction we were talking about earlier when we were using the activity series and determine which of these two directions is spontaneous. Is it spontaneous for nickel plus copper ions to give me nickel ions plus copper, or is it spontaneous for nickel ions plus copper to give me nickel metal plus copper ions? Well, I'm going to look at this thing and see which of these things is easier to reduce. Well, the copper is higher up. The more positive you are, the easier you are to reduce. So copper is easier to reduce than nickel. Relative to hydrogen, copper has a positive reduction potential and nickel has a negative reduction potential. And so because copper is higher on this list of reduction potentials in terms of the value of its reduction potential, it is easier to reduce. It will be the cathode, because remember reduction occurs at the cathode, and the nickel will be in the anode. And so the top reaction is going to be the spontaneous reaction. And we already know that because that is exactly what the activity series told us. However, now we can go on and calculate a cell potential for this cell. Okay, and the way that we do this is once we've decided what is going to be the cathode and what is going to be the anode in our cell, we simply use this equation. The cell potential for the entire cell is going to be the reduction potential of the half reaction that is the cathode minus the reduction potential of the half reaction that is the anode. And so for this reaction, the nickel half reaction is going to be the anode. Nickel is being oxidized. The copper half reaction is going to be the cathode. Copper is being reduced. And therefore, when I plug those numbers into that equation, the reduction potential for copper is positive 0.34. The reduction potential for nickel is negative 0.28. So 0.34 minus negative 0.28 is equal to 0.62 volts. That would be the reduction potential for this cell. You may recall when I built a cell in class, it was a copper zinc cell instead of a copper nickel cell. And if you calculate the reduction potential for that one, it would be 0.34 minus negative 0.76, which gives you 1.1 volt. And you might remember that I was very excited when we put the voltmeter into that cell and discovered that it was reading 1.1. So the cell potential for a spontaneous redox reaction will always be positive. If I reverse this reaction to give the reaction that we know is non-spontaneous and then did the same calculation, I would get negative 0.62 volts. So the spontaneous reaction is going to be the one that gives me a positive cell potential. Now, where do these numbers come from? How do we get these cell potentials for half reactions? Because a half reaction cannot occur on its own, right? You can't just have reduction without oxidation, and you can't have oxidation without reduction. Well, to do this, we use what's called a standard hydrogen electrode. And you'll notice if you go back through these things that hydrogen has been arbitrarily defined as having a reduction potential of 0. So regardless of which direction you go with this, either reducing hydrogen ions to give you hydrogen gas or oxidizing hydrogen gas to give you hydrogen ions, that is going to have a cell potential of 0. So the standard hydrogen electrode consists of a platinum electrode that has one atmosphere of pressure of hydrogen gas in it and a 1 molar concentration of hydrogen ions. And so you would have a 1 molar solution of some strong acid, like, say, nitric acid. By the way, I should mention that the standard conditions for determining reduction potentials are always solutes at a concentration of 1 molar and gases at a concentration of 1 atmosphere. So in the standard hydrogen electrode, you have 1 atmosphere of hydrogen gas and you have a 1 molar solution of H+. And so it could go either way, right? If it was acting as the anode where oxidation was occurring, then hydrogen gas would be oxidized to hydrogen ions. If it was acting as the cathode where reduction is occurring, then hydrogen ions would be reduced to hydrogen gas. And so what we do is we simply take this standard hydrogen electrode and we hook it up to the other half reaction whose potential we want to measure. And so here's an example with zinc. I simply take my standard hydrogen electrode and I hook it up in a cell with a zinc half reaction. And then I do two things. I look at what voltage the meter is telling me, what potential the meter is telling me that the cell has, and I'm looking for the direction that the electrons are flowing. So in this case, when I hook it up to zinc, the voltmeter reads 0.76 volts, and it tells me that zinc is acting as the anode and the standard hydrogen electrode is acting as the cathode. Okay, and so because zinc is being oxidized, not reduced, and therefore it is easier to reduce hydrogen than zinc, therefore it is harder to reduce zinc than hydrogen, then zinc gets a negative value. And so I would give this cell, I would give the half reaction for zinc as having the potential of negative 0.76 volts. Okay, and that's how we generate values like this, right? So when we make a cell of hydrogen and zinc, we get a voltage of 0.76, and hydrogen is the cathode, therefore it's negative 0.76. When I make a cell of copper and hydrogen, I get a voltage of 0.34, and copper is now acting as, and hydrogen is now acting as the anode, and copper is the cathode. So since copper is the cathode, it gets a positive value. And then if we make a cell of any two things that aren't hydrogen, the cell potential is simply going to be the difference between the two standard reduction potentials for the two half reactions, which is what we're doing when we do this operation. All right, let's go and just talk about a couple more things because this is getting a bit longer winded than I intended it for it to be. But you'll remember that I said that cell potential is an intensive property. And therefore, when we scale a reaction, we do not scale the voltage because voltage is again, energy per unit of charge. And so if I increase the scale of a reaction, the energy is going to go up, but also the number of units of charge are going to go up, and therefore the voltage stays constant. So let's look at an example of that. Here, as we've just seen, is the reduction potential. The standard reduction potential for zinc is negative 0.76 volts. The standard reduction potential for silver is positive 0.8. That means that silver is relative to hydrogen is pretty easy to reduce. So now if I make a cell out of zinc and silver, its cell potential is going to be the difference between these two numbers. It's going to be 0.8 minus negative 0.76. So you'll notice that I am doubling the scale. In order to balance the equation, I have to double the scale of the silver reduction, but I'm not doubling this to 1.6 volts and then subtracting negative 0.76. In other words, this is not 2.36, it's 1.56, because despite the fact that I am doubling the scale of the silver reaction, I am not doubling the potential of the half reaction because, again, cell potential is an intensive property. All right, final thing, a practice problem. So given the information here, the reduction potential for chromium-3 to chromium-0, which is negative 0.74, and the reduction potential from iron-2 to iron-0, whose reduction potential is negative 0.44. Determine the cell potential that I would get if I made a cell from these two things, an iron-chromium cell under standard conditions, and then determine which compartment would be the anode and which would be the cathode. You can go ahead and pause this if you want and think about it, and then turn it back on. So I'm actually going to answer the second question first, which is which compartment is going to be the cathode and which compartment is going to be the anode. Remember, I said when we were first talking about that table 20.1 and standard reduction potentials, that the more positive the standard reduction potential, the easier it is to reduce. So although both of these standard reduction potentials are negative, I can still say that this one, the one for iron, is more positive than the reduction potential for chromium. Therefore, iron is easier to reduce. That iron ions are easier to reduce than chromium ions. Therefore, chromium metal is easier to oxidize than iron metal. Therefore, iron will be the cathode and chromium will be the anode. So you can see here in my balanced equation, iron is being reduced. That's the cathode. Reduction occurs at the cathode. Chromium is being oxidized. Oxidation occurs at the anode. And then to calculate the cell potential, once more, I do not multiply by any coefficients when I do this because cell potential is an intensive property. So the E cell is going to be the reduction potential of the cathode, which is negative 0.44, minus the reduction potential of the anode, which is negative 0.74. Negative 0.44 minus negative 0.74 gives me positive 0.3 volts. That would be my cell potential. Okay, I managed to do this in just 20 minutes, and so we will have a QOD the next time we meet, and look for some practice problems posted along with the assignment as well. And thanks for watching.